Okay. To start the afternoon session, Professor Artur Hideyuki Tomita, we will talk to us about some properties between countable compactness and pseudocompactness in topological groups. Professor Artur has a doctorate in mathematical science from York University and currently works at the University of São Paulo. His line of research is general topology and set topology. Please, Professor, you can start.
Thank you for the invitation. So I will just turn off the video here. Okay. Oh, okay. Can you hear me?
Yes, yes, yes.
Okay, good. So, just a moment. Okay. So this talk is based on some works that I did with some people that I will mention them during the talk. At the end, if I have time, I'd like to give some sketch of some proofs that are more recent from this is my student that finished this year. Well, so I'll just mention here first the two results that I would like to mention afterwards. One is that assuming the existence of C incomparable selective ultrafilters, there exists a group G such that G to the n is countably pracompact for each n in omega, and such that G to omega is not countably pracompact. I will mention the definitions later. And the second one is assuming the existence of two to the continuum incomparable selective ultrafilters, there exists a group G such that G to the 2 to continuum is countably pracompact, and such that the next power, G to the 2 to continuum plus, is not countably pracompact. So starting with the definitions, we will consider spaces here Tikhonov, so Hausdorff and completely regular. And the topological group will be Hausdorff, thus also will be Tikhonov. So we denote the set of known principal phi ultrafilters omega by omega star. And also, well, I'm not really using this, but these are the finite subsets of omega, and these are the infinite, these are the finite subsets of X, and these are the countable subsets, infinite countable subsets of omega. So we say that space is pseudo-compact if every continuous real valued function on X is bounded. Space is countably compact if every infinite subset of X has accumulation point in X, and it's well known that countably compact implies pseudo-compact. And countably pracompact is if there exists a dense subset D in X such that every infinite subset of D has accumulation point in X. So here you don't require countable compactness, but you expect the space to have many accumulation points, right? Okay, so and it's useful to write the accumulation points using p-limits. So here, given an free ultrafilter in X and a sequence xn and in omega containing the space X, we say that X is the p-limit of the sequence xn. If for every neighborhood V of X, we have that the n's in omega such that xn belongs to V is an element of an ultrafilter, right? So this is natural if you compare with the convergence sequences, right? But then instead of using the ultrafilter, you take the filter of coinfinite, and then a convergence sequence would satisfy exactly this kind of property, right? But here we use outer filter, so it's not really related to convergence sequences. But definition, Gimbur and Sachs say that P in omega star, X in X, and a sequence Xn and in omega of non-empty subset of X, you say that X equals to the P limit of Xn. If for each neighborhood V of X, we have the indices such that the V intersects Xn is non-empty belongs to P. In the case that Xn is a singleton, then you have exactly the definition above here, right? Because intersecting here would mean that the single element would be an element of V. Okay, so and observe that an element X in X is accumulation point of a sequence if only if there exists an outer filter, a filter such that the X is a P limit. So finding the ultra filter that makes accumulation point a P limit gives us some information about how the sequence accumulates to this point. And we often use this for products or also to obtain some subspaces of interest. So using then P limits, we have these, right? X is countably compact if only if every sequence Xn containing X has a P limit for some ultrafilter. Here we don't require to be always the same ultrafilter, can be any ultrafilter. And then we have that X is countably precompact if only if there exists a dense subset D in X such that every sequence Xn and in omega containing D has a P limit in X for some P in omega star. And X is pseudocompact if only if every sequence UN and in omega of non-empty subsets of X has a P limit for some P in omega star. And finally, we define some space that is slightly stronger. In the previous definitions, for each sequence of points or open subsets, the only requirement is the existence of a P limit for some P. So if we want always the same P, then we have this definition here. No? Let P in omega star now is fixed. A topological space is P compact if every sequence Xn and in omega containing X has a P limit. And then Ginsburg and Sachs define what is P pseudocompact, which is similar. Right? So a topological space is called P pseudocompact if and only if every sequence UN and in omega of non-empty subsets of X has a P limit. And then this is the last definition that we're going to discuss that is also related to countable compactness and pseudocompactness. A topological space X is called selectively pseudocompact if for every sequence UN and in omega of non-empty subsets of X, there exists a sequence Xn and in omega containing X in X and P in omega star such that X equals to the P limit of Xn, and for each n in omega, Xn belongs to Un. So just remembering here that to be pseudocompact, it will suffice to have that this sequence here have a P limit, but in here you want not just you want a sequence that witnesses that UN of the P limit, right? Not just the open sets, but really a sequence. And these concepts are not the same, as we will mention later. So we have a we had the p-compact spaces are countably compact, which is just because here we use the witness is always the same p, right? Then countably compact implies countably pra-compact, also is immediate because the witness would be the whole space here. Then you have that countably pra-compact implies selectively pseudocompact because if you take family open sets, you take then the 1 point from each open set that is in the dense subset that witness countable pra-compactness, and then this sequence will have an accumulation point. And selectively pseudocompact also is immediate by definition. But, that selectively pseudocompact is pseudocompact. Now, to show that the arrows don't reverse, this sometimes is more complicated. So, at least for groups, right? So these are all for groups that I think I forgot to mention. So the reverse, let me see here. So that countably compact, p-compact, that countably compact does not imply p-compact for any p. This was a consequence of this result from Rushak and Bamil, I forgot the other name here, and Shela and Ramos Garcia. And then the third one here was proven by myself and my student that's in her thesis, which is that, oh, sorry, let me go back here. This one here, right? That countably compact, that selectively pseudocompact does not imply countably pra-compact. And then the fourth one was proven before. Also was this that example of a pseudocompact that is not selectively pseudocompact. These are all groups. Then, and for the second one, it's not difficult to see, so I just wrote here, but I'm not going to prove. You take the Z, the subgroup of X22 omega 1 Cartesian omega, and then you take the group generated by the elements that have countable support, union with the X in X, such that the support is basically omega 1 times omega. Then the group generated by this part here will be countably compact, so it's witnesses for countable pra-compactness. And then inside this part here, you have a sequence that converges to a point outside of the group, then it can't be countably compact. So the other ones are more complicated to prove, so I'm not going to mention how to construct the examples. But now some general questions we can consider about these properties as what cardinals admit a topological group with one of these properties? So for pseudocompact and countably compact, this has been studied for a longer time, but still we don't have a complete solution. And more specifically, also, what abelian groups admit a group topology with one of these properties? So this also, I think, is more evolved in the case of pseudocompactness. And for countable compactness, there are some cases, and in the other ones, I think we're not studied so much. And the other thing would be the groups that admit a group topology with one of these properties also admits one which in addition has no non-trivial convergence sequences. This particular is interesting for countably compact, but maybe for the other cases as well. And the last one that this is what we're going to mention afterwards is how these properties behave in terms of products. So I'll just mention quickly some results related to these other questions, and then we go to products. So these questions all arose from compact groups, because compactness is stronger than any of the properties mentioned before. Compactness is productive. Compact groups have non-trivial convergence sequences. So it then became, first the question was whether pseudocompact groups would also have would have non-trivial convergence sequences. This is in the 1960s. But then afterwards in the 80s was about countable compact groups and so on. And it has been studied, and it also has been studied about classifying the abelian groups that admit compact group topology. So now we're trying to see what happens for these other properties related to countable compact and pseudocompact and so on. So about cardinality, and myself and Castro Pereira showed that under a condition weaker than GCH, that all torsion groups could classify all the torsion groups that admit countable compact group topology. And then more recently, this is 2 or 3 years ago, we showed that the sum of Qs admit p-compact group topology without non-trivial convergence sequences. So this is some large examples, but you use selective ultrafilters, which do not exist in ZFC. And well, Tkachenko showed in 1990 that there exists a free abelian group of cardinality C using the continuum hypothesis. And then also this was 2 years ago, or I think Bellini, Hart, Rodriguez, and myself show that the free abelian group of cardinality kappa equals to kappa omega greater or equal to 2 omega admits a countably compact group topology and also trivial convergence sequences if they are C incomparable selective ultrafilters. So, and the first example of a countably compact group without non-trivial convergence sequences was obtained in the 1976 by Heinau and Juhas. And Rushak, Van Mil, Ramos Garcia, and Shala, they were the first to show that there exists a countably compact group without non-trivial convergence sequences of cardinality continuum in ZFC. Oh, sorry. Let me continue here. Okay. Then also this is in my student thesis. We made a modification of this example here to obtain one of cardinality to the continuum. But here we used weak p points, and then this construction cannot go up, right? Well, so and then we have these questions that are still open in ZFC. If it's unknown if the X is larger than 2 continuum, right? Countably compact groups without non-trivial convergence sequences. And also it's unknown if there exists one example in ZFC that is non-torsion, because this example has order 2. And then also Van Douwen showed that it's consistent that the average pseudocompact group has cardinality of uncountable cofinality. And this is in the also result from 2001. We show that there exists a countably compact group whose cardinality has countable cofinality using forcing. Also about cardinality. So that there exists one example of cardinality of this whose cardinality has countable finality using instead of the Boolean group, a free abelian group. And now about classification, the pseudocompactness has been studied by many researchers in the 80s, and Jikarnian and Shakhmatov have written a book on the subject. And then in the case of countably compact, Jikarnian and Kachenko classified the abelian groups of cardinality C that admits a countably compact group topology without non-trivial convergent sequences. But using MA, I forgot to include Martin's axiom here. So it's not known yet if this works in ZFC, right? Our classification. Because we don't know if there are non-torsion abelian countably compact abelian groups in ZFC. So, and Jikarnian and Shakhmatov obtained the classification of the groups of cardinality less or equal to 2 to continuum that admit a countably compact group topology without non-trivial convergent sequences. Also using forcing. The forcing is similar to this type of forcing that was used here, but there are more conditions and it's more complicated. But the starting forcing has some similarities, and because of that, also the forcing makes the construction stop at 2 to continuum. You cannot go higher using this particular forcing. And now the remainder of this talk, we talk about the product. So first, since we are going to use selective ultrafilters for the construction, then we will just mention what is a selective ultrafilter. A selective ultrafilter on omega is a free ultrafilter P on omega such that for every partition AN and in omega of omega, either one of ANs is an element of the ultrafilter, or you can pick one point. There exists one point from each element of ultrafilter of this partition that is in the ultrafilter. So either AN is in the ultrafilter, or there exists a B that hits exactly AN in one point. So that will give the name selective. So the existence of selective ultrafilters is independent of the usual axioms. And for example, Martin's axiom implies the existence of 2 to continuum selective ultrafilters. And there is a model of ZLC in which there are no selective ultrafilters. And here, well, just to mention a little bit about selective ultrafilters. So here we have the Rudin-Kisling ordering, and then you say that P and Q, P less than Q Rudin-Kisling if there exists F omega into omega, so that F star of Q equals to P, where F star P is defined up here. And this is a pre-order on omega star. And we say that P and Q are incomparable if neither P is less or equal than Q, nor Q is less or equal than P. And selective ultrafilter are exactly the minimal elements of the Rudin-Kisling order. Now, about products, pseudocompactness is not preserved on the products for arbitrary topological spaces. This was shown by Terosaka and also Novak in 1953, independently. Nevertheless, Comfort and Ross show that the product of a family of pseudocompact topological groups is pseudocompact. And this result led Comfort to ask whether there are countably compact topological groups whose product is not countably compact. More generally, in 1990, he asked the following question in the survey Open Problems in Topology. Is there, for every non-necessarily infinite cardinal number alpha less or equal to the continuum, a topological group G such that G to the gamma is countably compact for all cardinals gamma less than alpha, but G to the alpha is not countably compact? So when exactly you change, there's a change of behavior in the power, right? So if you take smaller products smaller than alpha, then it's going to be countably compact, and if you take exactly alpha, then it's not countably compact anymore. And obviously, if you take a product that's not countably compact, then larger power is also not countably compact. So it's known that if G to the continuum, G to the two continuum is countably compact, then G to the kappa is countably compact, and that's the reason that here appears to continue. This is the result of Ginsburg and Sachs. In fact, I think, if I'm not mistaken, confirmation that this was implicit in their proof, and then he includes this comment in the MathSciNet. Well, so we now list some advances that have been made in this subject over the years about this question. Then the first, Van Douwen was the first to prove consistently that there exist two countably compact groups whose product is not countably compact. And in general, comfort question was answered positively in 2005 using 2-3 continuum selective Artur filters, and using that 2-3 continuum equals to 2-3 less than 2-3 continuum. And finally, in 2021, it was proven in the FC for the first time that there exist two countably compact groups whose product is not countably compact. So, the examples mentioned here, so there's 3 examples, they're all of order 2. So they are Boolean. It's still open if there exists a countably compact group topology in a free abelian group in ZFC. Now examples are here, which I'm not going to mention here. And then this was also my former student. We show that it's in her thesis. We show that under the existence of selective Artur filters, there exists a free abelian group whose square is not countably compact, and later using some improvement of this technique, it was shown that there exists a topological free abelian group whose finite powers are countably compact, also using select Artur filters. In the case of free abelian groups, in fact, you cannot go beyond this because the omega power of a free abelian group is no longer countably compact. So this is the best you can get for free abelian groups. So this is not a good candidate to solve conference question for using it is not a good non-torsion group to obtain results like the conference question. Okay. So now it's natural to ask also productivity questions for other types of properties, right? Such as countably pracompact groups. More generally, one can ask a comfort-like question for countably compact groups, countably pracompact groups, right? For each cardinals alpha, there exists a topological group G such that G to the gamma is countably pracompact for all cardinals gamma less than alpha, but G to the alpha is not countably compact. Note that in Comfort's question, here we have this limitation to the continuum because of this result here. At first, we thought that maybe to the continuum also would be a limitation, but as we will see later, it's not the case. So we don't know if there is a limitation. So in this regard, in 2018, under CH, showed that there exists a topological group G, for which G2 kappa is countably compact, but G kappa plus 1 is not selectively pseudo-compact. Well, since countably compactness implies selectively pseudo-compact, and not being selectively pseudo-compact is stronger than not being countably compact. And then we try to use Hrushak et al. Example to obtain one in ZFC, but we did not make progress on it. So it's still open if you can do something like this, even for two, right? And then sorry, let me move here. Bardia, Ravisky, Zonsky construct under MA a Boolean countably compact topological whose square is not countably pra-compact. Here's an observation, just that if GT omega is countably compact, then you have that every power will be countably pra-compact. So if you want to build something, it can the countable power cannot be countably compact, for example. It's not known yet in ZFC whether it's true that countable compact is non-productive in the class of topological groups. So the only examples we have are not in ZFC. So here we'll just mention first about this case here. Suppose that there are syncomparable selective ultrafilters, then there exists a group G which has all finite powers countably pra-compact, and such that G2 omega is not countably pra-compact. So previously with Garcia, we got only for finite powers, and here we have the first to go to infinite. So we do not know if you can not countably pra-compact or not selectively pseudo-compact. So we're going to start commenting on this construction here. So usually this involves the Boolean group with using C less than omega with this symmetric difference as a group operation. This is homeomorphic to taking the direct sums of two. And it is choosing a subfamily, a suitable family A of homomorphisms that will generate the topology, and then these homomorphisms. Basically, you make promises about that the sequences will have a certain point as a p limit, and then the homomorphisms must keep this promise. So in the end, you have enough accumulation points to get the property you want. And then to obtain these homomorphisms, you need some lemmas of existence. So here's what was mentioned before, right? So usually what you want is these, right? One that the homomorphism will satisfy this kind of property. So for the sequence xn and in omega, you fix that x will be the the singleton C will be the p-limit of a sequence, and then every time you use the homomorphism, this homomorphism you have to satisfy these, so that in the end, really, the unitary, the singleton C will be the p-limit of the xn, because this C with the phi's will be the coordinates of the group. And then you use a induced topology to get the topology on the group. So we enumerate our sequence. We want to pre-assign p-limits in a way that they can be extended from a countable homomorphism to a homomorphism G. This is done in most constructions now. The topology on G is the topology generated by appropriate family homomorphisms that keep the promises about these pre-assigned p-limits. And since we want to make certain sets dense, we do not take all the possible homomorphisms, usually limiting the number of homomorphisms to G2 omega. However, we have to properly choose the accumulation points of each sequence and also the outer filters associated in order to guarantee that small powers are countably compact. So somehow you have to make sure that small products have accumulation, have p-limits, but then when you add new coordinates, you have to make sure that if you add new coordinates, then it should fail to be a p-limit. So it's a little bit tricky to do that. And then this was used for using selective ultrafilter. This is the way we produce the homomorphism. In the case that of Hrushak et al., they construct a special ultrafilter that will guarantee that you have the homomorphisms, but then you have less control about making a sequence not being not being a p-limit. And then because of this, I mean, you obviously you get a result in ZFC, but it makes it harder to make to know if the larger product will or will not be countably compact or some other property. Sorry. So this is the idea to make the sequence not to be countably compact. Sorry, for a sequence not to be the accumulation point, you just make sure that this it is one of the coordinates witness this. So there will be a phi that right. So in the case, since we don't want any dense subset to witness countable precompactness, then you have to somehow every dense subset in a larger power must be you have to make sure that somehow the dense has a larger power. They are too large in a sense that some of the sequence will fail to have an accumulation point. So you have to really kill many sequences to not have too many accumulation points in a sense. So In the previous work with Fraga, we construct a selective pseudocompact group that was not countably pra-compact, and there we really this was the idea that you avoid the small dense subsets, so the group was not separable, because then once the dense subsets were larger, then it was easier to make it to fail to have an accumulation point for one of the sequences. And well, I think I have more 10 minutes, so maybe I won't have time to explain too much here. Then, okay, let's see. Let me skip this a little bit. Yeah. So the idea here was that the small products, every time you add a new coordinate, somehow some sequences must stop. The larger sequence must not have accumulation point. So you have to kill the p limits for a growing number of ultrafilters. But then at the same time, there should be enough to have every finite power have enough p limits, and then somehow you just fix which ultrafilters will work for a finite power, and then the other larger power will be some different candidate that you're going to use. And then when you put them together, the sequences that are in one and the other, you will not have any accumulation points. So in a sense, like some small parts will have powers. The powers will have finite powers will have accumulation points. But when you take a sequence in one part for one power, finite power, and then the other witness for the other finite power, you just use the same technique that you used to show that the square is not countably compact. But yeah. And oh, okay. So for this, basically, we call what is in the support of G would be just that you use exactly xn you use for the nth power to have a witness for that G to the n is countably pre-compact, and then you xn in xm for n different from m will be disjoint, and I mean they generate the groups that are a direct sum. Right? So the intersection of both is just the zero, the identity, and then the behavior of each one here. I mean, when you take a sequence that is xn in a sequence in xm, if you put them together, they don't have accumulation points. But then you have some cases, and then so for example, you take when you take a dense subset, called the support of the support of G, such that G belongs to the projection in D, and then we had that the support is finite or infinite, and in both cases you get a situation that that the originals, you can find a sequence in the countable power that will not have an accumulation point, and somehow it's a little bit like a pigeonhole principle, but not exactly. And then here, and then for the case to the continuum plus, then you use for every small product, you basically you do the same. You partition the G into two to the continuum many sets, and then each part will make sure that the smaller product is sorry. You make sure that you define each coordinate will you use one of will be taken off by one piece here, and then you make sure that every sequence in G to the continue. Sorry. You pick once to continue many sequences in the inside this product. Have accumulation point that you use each auto filter. You're going to use only once for each piece here. For each coordinate, it's going to be exactly the idea is to have exactly only one sequence that uses this auto filter, so that when you start to mix things, when you get a larger a dense subset in the larger product, then necessarily you have repetitions in that will make the sequence not have a accumulation. You're going to find a sequence in this dense set that in the larger product that doesn't have a accumulation point. So okay. So the idea is more or less similar to the one for finite case, but it's more complicated because then you cannot you use for each coordinate you need a p limit. In the other case, each coordinate the p limits for only one coordinate, because then you expand it and you have for the finite power using just basically one of elements of the partition. Okay. And well, I think I have only a few minutes, so yeah, I think probably I could not explain exactly the idea, but if anyone wants this work is already published, so you can read the details there. And then skip here. And thank you for your attention.
Thank you very much. Is there a question for Professor Artur? We have 10 minutes for questions. ¿Alguna pregunta para el profesor? Pueden usar el chat. Parece que no. Well, again, thank you very much, Professor.
Thank you for the invitation.
Please.
Okay.
1 minute, please. Okay. Listo, Kevin. Okay, at this time, we present the certificate of Professor Artur. Thank you for your participation in this third International Congress on Topology and related topics. Again, thank you very much.
Thank you.
Bueno, continuaremos en 10 minutos y le cedo los micrófonos para la siguiente presentación al profesor Luis Durán. Entonces, pues aquí estaremos. Gracias.
Ojos azules, no llores, no llores ni te enamores.
Ojos azules, no llores, no llores ni te enamores.
Llorarás cuando me vaya, cuando remedio no haya.
Llorarás cuando me vaya, cuando remedio no haya.
Tú me juraste quererme, quererme toda la vida.
Tú me juraste quererme, quererme toda la vida.
No han pasado 2, 3 días, tú te alejas y me dejas.
No han pasado 2, 3 días, tú te alejas y me dejas.
Adiós pueblo de Ayacucho, perlas Chayaya, me voy, ya me estoy yendo, perlas Chayaya.
Adiós pueblo de Ayacucho, perlas Chayaya, me voy, ya me estoy yendo, perlas Chayaya. Ciertas malas voluntades, perlas Chayaya, hacen que yo me retire, perlas Chayaya.
Ciertas malas voluntades, perlas Chayaya, hacen que yo me retire, perlas Chayaya. Oye, ¿y en quechua cómo sonaría?